Alright, so this is the second problem. We'll calculate the pressure drop and head loss in a pipe. So this is the schematic here given. You can see the diameter is given, the velocity here is given, and the length of the pipe it is given here. The water temperature is 5 degrees centigrade. The density, the viscosity, all the properties are given. And so we need to calculate the head loss, the pressure drop, and the pumping power. So from this question, we are going to calculate, the head loss, the pressure drop, and the pumping power. So if we write down the assumptions, as usual, we'll write this is a steady flow, okay, steady and incompressible, okay. So this is steady and incompressible flow, and we'll say that the entrance effects are negligible. So the flow is fully developed. The same thing like what we did for previous problem. So for the fully developed flow. And the third one is this is, we'll say the pipe contains no component like bends, valves, or the connectors, okay. So I'm not just writing here. So no bends, no valves, no connectors. So that's all the assumptions. Now the properties here given. The density is 1000 kg per meter cube. The viscosity, the dynamic viscosity is kg per meter second. So that's given in this problem. We need to calculate, the first thing is we need to calculate the head loss, okay. So we know the head loss formula. So head loss H L, this is equal, we know F L over D B square over 2G, okay. So you may you may find this is quite similar like the pressure drop, but we'll discuss it later. You'll see we have very small differences between these two formula, like the head loss and the pressure drop. Anyways, for head loss we know F L over D B square 2G. So that means to solve this we need F, the friction factor. If the flow is laminar, then it is 64 over Reynolds number. So that means we need to calculate the Reynolds number, right? So that's the overall flow chart we need to follow for the first part of this problem. So at first we will calculate the Reynolds number, and we know the Reynolds number RE, this is equal the density, velocity, diameter, and viscosity. Density is 1000 given. Velocity is 9. Diameter 0.3 centimeters, so 003 meter. And the viscosity 1.519 10 to the power minus 3. So the Reynolds number we'll get here is 1777. So this is the Reynolds number. So that means it is actually less than 2300, the critical Reynolds number value. So that means the flow is, we can say it is laminar flow. When it is laminar flow, we can easily use this friction factor formula. So if we substitute that value here, the F, it is equal 64 RE, or this is 64 RE 1777. So this is 0.0360. This is F. Now let's calculate the HL, the head loss. So HL, the head loss, this is equal F L over D B square 2G. F is 0.0360. Length, the length of the pipe is 9 meter. Diameter is 0.003. V square is 0.9. Velocity is 0.9, and the gravity 2 into 9.81 or 9.8. So if we solve this, we'll get it is 4.46 meter. So this is HL, that means the head loss. So we calculated the head loss. So the second part of the problem is we need to calculate the pressure drop. So here this pipe will solve the second part of this problem, that means the pressure drop. So this pipe, this is a horizontal pipe, okay, and its diameter is 0.3 centimeter constant. So that means the pressure, the pressure drop in this pipe, it is actually due to the friction losses, okay, nothing else, and which is equivalent to the pressure loss. So we can say the pressure drop delta P, this is equal to the pressure loss, which is F L over D, and the density velocity square over 2. You will see the basic differences here. It is 2g and we had no density over there. Anyways, so F 0.0360, length 9 meter, diameter 0.003, density 1000, velocity 0.9, this is square over 2. So if we just convert it into Newton, sorry, we need it in kPa or Newton per meter square. So 1 Newton equal 1 kg meter per second square. So we'll get this value is 43,740 Newton per meter square, or we can say 43.7 kPa. So that's the pressure drop we have got. This is the second part of this problem. In the last for us, we need to calculate the volume flow rate and the pumping power. Now the question is calculate the pumping power. See, so we need to calculate the pumping power. So for pumping power, we know the formula is the volume flow rate into delta P, right? The volume flow rate delta P. So we don't know the volume flow rate, so let's calculate it. So the volume flow rate, it is the velocity, average velocity into cross-sectional area. Average velocity is 0.9 and the area is pi d square over 4. So this is 0.9, okay, into pi, diameter is 0.003, this is squared over 4. So we'll get this is 6.36 into 10 to the power minus 6 meter cube per second. So this is the volume flow rate. We'll get the volume flow rate here. Now the pump power, which is the V dot and what it is, delta P. So the volume flow rate is 6.36 10 to the power minus 6, and the pressure drop we know 43,740 Newton per meter square. So if we convert it into watt, like 1 watt equal 1 Newton, 1 Newton meter per second. So then it will be 0.28 watt. So this is the pumping power. So we can say this is the pumping power. So this amount of power we actually need to overcome the friction loss. Actually, it is due to the viscosity here, and nothing else are working. So this is the the pumping power. So this is the second problem.